Hello, students. Welcome back. Today, we are going to dive into the anatomy of chemical change and decode the fascinating microscopic rules that govern our macroscopic reality. Let's find out how the world changes at an atomic level. Think about what happens when milk is left out in the summer, an iron tawa or pan rusts in humid air, or even when we breathe. In all these daily situations, the initial substance permanently changes its identity. This irreversible change is the signature of a chemical reaction. But how do we know a reaction has actually taken place? Look for these 4 key pieces of evidence. Change in state, like a solid magnesium ribbon burning into powdery ash. Change in color, like green ferrous sulfate crystals turning brown upon heating. Evolution of a gas. Notice the hydrogen bubbles forming around zinc granules in dilute acid. Change in temperature, like a conical flask becoming hot to the touch during an exothermic process. To write this down neatly, we use chemical equations. On the left-hand side, we have our reactants, the initial substances undergoing the change. The arrow points in the direction of the transformation, leading us to the right-hand side, where our entirely new products sit. Keep in mind, this basic equation is called a skeletal equation because the math isn't balanced just yet. Now, why must we balance it? Because of the absolute iron rule of chemistry. The law of conservation of mass can neither be created nor destroyed in a chemical reaction. This means the atomic ledger must balance perfectly. The number of atoms for each element must be exactly the same before and after the reaction. Let's learn how to balance using the hit-and trial method. Step 1 is the lockdown. Draw boxes around each formula and never alter anything inside them. Steps 2 and 3 involve the audit. List out the number of atoms on the left-hand side versus the right-hand side. Always start balancing with the compound containing the maximum number of atoms, in this case, iron oxide. Let's target oxygen first. Moving to steps 4 and 5, the multipliers. We use the smallest whole number coefficients to multiply the entire molecule from the outside. Finally, step 6 is the final tally. Look at that. 3 iron, 8 hydrogen, and 4 oxygen atoms on both sides. Our atomic ledger perfectly matches. To make our equations even more informative, we add physical states. S for solid, L for liquid, G for gas, and AC for aqueous solutions dissolved in water. Any specific reaction conditions, like sunlight, heat, pressure, or catalysts like chlorophyll, are written directly above or below the arrow to show the exact environment needed for the transformation. Chemical reactions generally fall into a few predictable patterns, or archetypes. We have combination, decomposition, displacement, double displacement, and redox reactions. Let's explore each of these beautiful blueprints one by one. First up, combination reactions. This is where 2 or more substances forge a single new product. Think of whitewashing, where quicklime reacts vigorously with water to form slaked lime, releasing intense heat. Because they release energy, combination reactions are frequently classified as exothermic. Next is the exact opposite, decomposition reactions, where a single reactant breaks down into multiple outputs. This requires an input of energy, making them endothermic. This energy can come from heat, like breaking down limestone into quicklime, electricity, like splitting water into hydrogen and oxygen, or light, like silver chloride turning gray in sunlight, a reaction famously used in old black and white photography. Now let's look at displacement reactions. Think of this as an atomic partner swap. A more reactive metal will physically evict a less reactive metal from its compound. When you place blue-colored copper sulfate solution with iron nails, the iron displaces the copper, turning the solution green and leaving a reddish-brown copper deposit on the nails. In double displacement reactions, there is a mutual exchange of ions between the reactants. When sodium sulfate and barium chloride mix, the barium and sulfate ions crash together to form barium sulfate. This forms an insoluble white solid that settles out of the solution, which we call a precipitate. Welcome to the redox seesaw. Oxidation occurs when a substance gains oxygen or loses hydrogen. Reduction is the exact opposite, losing oxygen or gaining hydrogen. Because electrons are transferred, one cannot happen without the other. They are irrevocably paired as reduction-oxidation, or redox reactions. What happens when these microreactions show up in the macro world? First, we get corrosion. When metals are attacked by moisture, acids, or oxygen, they slowly oxidize. Iron develops a destructive reddish-brown rust, copper turns green, and silver tarnishes black. Corrosion is simply a slow, relentless redox reaction destroying our infrastructure. The second major consequence is rancidity. When the fats and oils in our food oxidize over time, they spoil, completely changing in taste and smell. To fight this, food engineers use airtight containers, add chemical antioxidants, or flush bags of potato chips with unreactive nitrogen gas to push out oxygen and halt the reaction entirely. As we wrap up, look at this copper reaction. It is a combination reaction, an endothermic process, and an oxidation reaction all at once. Nature does not neatly separate reactions into textbook boxes. Every change we see, from a rusting nail to the very breath in our lungs, is woven from the exact same fundamental rules of atomic reshaping. Keep observing, keep learning, and I'll see you in the next video.